Unit 4 is on probability. Let's start with what seems reasonable to start with is what is probability? According to definition in our textbook, probability is a numerical measure between 0 and 1 that describes the likelihood that an event will occur. All right, so probability is a measure of how likely some kind of an event is to occur. Now, probabilities closer to 1 indicate that if the event is more likely to occur. Probabilities closer to 0 means it's less likely to occur. Now, some notation. If I write P for probability in parentheses, put an A, this is going to indicate that we read this P of A, right? Just like a function in algebra, P of A, F of X. This denotes the probability of an event A. This is the probability of an event A. And you can see here, if the probability of A is 1, that means it's certain to occur, and if it's 0, it will never occur. And here are 3 ways to make probability assignments. That means to assign a probability to some event. First of all, you could just do it by intuition. That just means, your past experience. You pick a number based on your past experience, your judgment, and your opinion. Okay, another way, number 2 here, is to think about relative frequency. Now, the relative frequency, here's what relative frequency is. You take a look at how often something occurs. We'll call that frequency, right? And then N is the total number of times that you observe it. Now, we did this in the first section when we were looking at making frequency tables. But now we're going to look at it again. Relative frequency says relative to the entire collection of observations, how often does yours occur? All right, so you would just say the probability of some event is this many times out of this many times. So suppose you perform some experiment and some particular event occurs 15 times out of, say you do this experiment 100 times. All right, so in this case, N would be 100, right? You perform the experiment 100 times. How often does this event occur? 15 times. So we will say that the probability of this event is, okay, now it's going to be the frequency divided by the total number of times you did it, relative frequency, and that's going to be 15 out of 100, or if you like decimals, you could say 15. Now I'm going to say this. This is the probability. Probability is a number, right, between 0 and 1. All right, this is a number between 0 and 1. Sometimes you might see probability maybe written as 15%. That just means 15% of the time it's going to happen. But I think if you're asked for a probability, write a decimal, all right? So in terms of probability, make that a decimal. If you're asked for a percent, then go ahead and change it to a percent. And now another way, this is number 3 down here, probability assignment based on equally likely outcomes. All right, so if you have, say, some kind of an event where every outcome is equally likely, then the probability is going to be the total number of outcomes favorable divided by the total number of outcomes. Let's do an example. Let's label this one up here number 2 so we don't get confused, and this will be number 3. All right, what if you did this? Just a real simple one. Toss a single die, all right, once, and observe the number. I won't write it all. Toss a single die once and observe the number on the top face. What is the probability of getting, say, a 2? Well, here's the outcomes, right? I'm going to call this S for sample space. Here's the set of all possible outcomes. If you toss a die once, what could possibly happen? You could get a 1, a 2, a 3, a 4, a 5, or a 6. And I'm going to claim that if the die is fair, all of these events are equally likely. You're just as likely to get a 1 as a 5. So what would you say the probability of a 2 is? Right? It's a fraction. Probability is a fraction. Now, when I do probabilities, I'm just in the habit of doing the denominator first. I always do the denominator first. What's the total number of outcomes here? Well, here's what could possibly happen. You could get any one of these 6 outcomes. All right, so total number of outcomes, 6. And in this case, And the numerator, that's the number of outcomes favorable to our event. Now, our event is getting a 2. There is only one way to get a 2. So the probability of getting a 2 is 1/6, or if you like, convert it to a decimal. Here's another example. You know what I'll do is I'll get us some room, and I'll erase this one up here. And let's say, what is the probability now of getting, say, what's the probability of getting a 4 or a 5? Well, now, as long as the events are equally likely, denominator first, 6 possible outcomes, and how many of these events, right, I'm down here now, how many of these events are favorable to our event, our outcome? Well, there's 2 of them, right? I could get a 4 or a 5. So this is going to be 2/6. I could make that 1/3, or if you like, leave it as 2/6. So if we say that the probability of some event A is 0.85, what we're thinking is that if we perform the experiment, there's an 85% chance that A will occur. Or another way of looking at it is, if we perform an experiment, say 100 times, then we expect to see the event A about 85 of those 100 times. Suppose that A is some event. We'll do an example in a minute. But just suppose A is some event, the complement of A, and here's how we're going to denote that. Actually, there are several ways to note, just depending on who you're talking to. I'm going to do it A prime. Some people do it A bar. Some people do it A with a C up here for complement. All right, but anyway, back to what we're doing. Suppose A is some event. The complement of A, I'll use A prime, is the event not A. So either A happens or it doesn't happen. They're complements of each other. So a simple example. Suppose here's the sample space, the set of all possible outcomes to toss a die once. Okay, so our example. Toss a die once and observe the number on the top face. So what could you get? A 1, 2, 3, 4, or 5. Now, suppose that the event A is getting a 1 or a 2. Now, what's the probability of A? Well, there's 6 possible outcomes, and there's 2 ways we could get that. So the probability of A is 2/6. Now, what is A complement? All right, A complement, all right, this is everything that's in your sample space that's not in A. All right, so A is 1, 2, so not A is 3, 4, 5, 6. And what is the probability of not A? Well, by relative frequencies, there's 6 elements in the sample space. 1, 2, 3, 4, 5. Oh, I forgot the 6 up here. And then there's 4 ways of getting that. Now you'll notice here that 2/6 plus 4/6 is 6/6, because, which is 1. And if I write this, what's the probability that A occurs or A does not occur? Well, that has to be 1, right? Either A occurs or it doesn't occur. Something has to happen. Now I could write this. The probability of A prime is equal to 1 minus the probability of A. Does that make sense? So in our example, what's the probability of A prime? Well, it's 4/6, but I could write that like this. Probability of A prime is 1 minus the probability, I'm over here. What is probability of A not happening? Is 1 minus the probability that it does happen. Probability that it does happen is 2/6, so there's my 4/6. Let's do some exercises out of the section in 4.1. So just do some homework problems. So how about this one? This is actually number 5 out of the textbook, but I'm not going to write 5 because sometimes they change editions. So you can probably find it. It's an interpretation problem. So suppose this. A Harris poll indicated that of those adults who drive and have a cell phone, the probability that a driver between 18 and 24 sends or reads text is 0.51. All right, so here's what they're saying. They take a look at drivers between 18 and 24, and they're saying that the probability of those people sending or reading text is 0.51. So then the question is, can this probability be applied to all drivers? All right, so can you apply this probability to all drivers? So think about it for a minute and then maybe put this on pause, think about it, and then come back and then we'll do it together. Well, I'm thinking that the answer is no, because that 0.51, that applies only to drivers that are in this age group, 18 to 24. Let's try another problem. This turns out to be problem 7 in my book. But if not, you can probably find it by the name here. Here's the problem. A recent Harris Poll survey of 1,010 adults selected at random showed that 627 considered the occupation of firefighter to have very great prestige. So estimate the probability to the nearest hundredth that a U.S. adult selected at random thinks the occupation of firefighter has very greatest prestige. Okay, well, it looks to me here like the sample is what? Out of 1,010 U.S. adults. And what we want to know is if we take a U.S. adult at random, right, so we're taking somebody out of our population. So think about it for a minute. Pause. Come back. And we'll do this one together. So I'm going to say that we've got a relative frequency going on here, right? Out of 1,010 adults, 627 consider a firefighter has great prestige as an occupation. So how about if we write this as, all right, I like to write denominators first, so 1,010, and the number of elements favorable to our event is, what, 627. All right, now, if I do this on my calculator, I'm going to round off a bit. So I'm going to get 0.0, what's it say, to round off to the nearest hundredth. I'll go with, let me change that then. It's going to be a 6.2, right? 0.62. Let's try another problem. How about this? An investment opportunity boasts that the chance of doubling your money in 3 years is 95%. However, when you research the details of this investment, you estimate there is a 3% chance that you could lose your entire investment. So based on this information, are you certain to make money on this investment? Okay, so what does this say? Are we certain to make money on this investment? Well, what does this say? An investment boasts that the chance of doubling your money in 3 years is 95%. So what do you think? Put it on pause, come back, we'll do it together. All right, well, I'm going to say we are not, right? We are not certain to make money. Even though there's a high likelihood, because it's 95%, that we will make money, there's also a chance that we could lose all our money, right? There's a 3% chance we could lose everything. So there's not 100% that we're going to make money on this. Now we've got an experiment. We're going to toss a coin 3 times, and part A says list the equally likely events for the sample space. Now, the sample space is this. I'll write S for sample space. This is going to be the list of all the possible outcomes. Here's one, right? So what are we doing? We're going to toss a coin 3 times, and what it tells us for each coin, any coin at all, the possible outcomes are heads or tails. The thing's not going to land on the side. So what could happen if you toss a coin 3 times? Here's one possibility, and I'll just put them in order. First, you get a head. Then the second toss, you get a head. The third toss, you get a head. Now, there's some other possibilities. Can you list them all? So think about it. Maybe pause, come back, and we'll do it together. Here's what I think could happen. You get head, head, head. Head on the first, head on the second, head on the third, head on the first, head on the second, tail on the first. Maybe a head on the first, a tail on the second, a tail on the third. Maybe you get tail, 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 tail on all 3. Or you get maybe a tail on the first, tail on the second, head on the third. Now the order doesn't make any difference. We're just listing all the possible things that could happen. You could get what? A tail on the first, a head on the second, a head on the third. Anything else? So anything else could happen here? Yeah, I don't think I've listed this one. You could get a tail on the first, a head on the second, a tail on the third, and for that matter, you could get a head on the first, a tail on the second, and a head on the third. I think that's it. So let me count them up here. 1, 2, 3, 4, 5, 6, 7, 8. And I'm going to write it this way. They're not asking this, but I'm going to say n for the number of elements in the sample space is 8. There's 8 possible outcomes when you perform this experiment, tossing one coin 3 times. Now, part B says this. This is part B. That was part A. Part B says, what's the probability that all 3 coins come up heads? Now, this is a relative frequency problem. What do you think it is? Give it a try. Come back. We'll do it together. So I'm thinking this. The probability of getting 3 heads, now that would be this event here, right? Probability of 3 heads. Okay, well look, there's 8 possible things that could happen, and only one of them, this one here, has the 3 heads, so I think it's 1/8. Now we also want this one here, right? It says, down here, compute the probability that there will be at least 1 tail. Now there's 2 ways to do this, right? Here's what we could do. The probability of at least 1 tail is, all right, there's 8 possible things that could happen. Now, how many of these up here have at least 1 tail in them? All right, just count them. Anything that has a T in it. 1, 2, 3, 4, 5, 6, 7, right? At least 1 tail means there's at least 1 T in there. So I could write it as 7/8. Or I could write it like this. What's the probability of at least 1 tail? All right, that's going to be the opposite, the complement of getting no heads, right? What's the opposite of no heads? At least 1 tail. Now, this is the complement, so I can write 1 minus, all right, probability of all heads. This is going to be 1 minus, that was 1/8, so this turns out to be 7/8. This is my problem 19 in my book, maybe the same for you in your book. Here's the problem. Some information. When do creative people get their best ideas? So this came out of a USA survey of 966 inventors. All right, information right away. I know N is equal to 966. I'm going to write it down so I've got it in front of me. Now, here's what we know. Time of the day. All right, so between 6 a.m. and noon, 290 of those 966 inventors got their best idea. Okay, 135 between noon and 6 of those 966. All right, so what do we ask for here? Part A, assuming that the time intervals include the left and the right-hand limits. Okay, wait a minute. Assuming that the time intervals include the left limit and all the times up to but not including the right limit. All right, so in the first one, you include 6 a.m., but right to not quite noon. All right, noon goes into the next one. All right, so then noon to almost 6, and so on. All right, so what do we ask for? Estimate the probability that an inventor has the best idea during each time interval. All right, so for the first one, what is the probability that we're between 6 a.m. and, say, 12 noon? I'll just write it that way. Can you see what that one's going to be? Actually, why don't you do all these and then come back and we'll see if we get the same answers. All right, well, I think they're all equally likely. So I'm going to say 966 altogether. And how many in that event? How many in this group here? 290. So I'm going to think that's 290 divided by 966. Now, when I did that on my calculator, here's what I got. I got 0.30020 ... Okay, now we need to round off to someplace. It doesn't tell us where to round off, but I'm going to say that this is, say, equal to 0.30, all right? Or there's a 30% chance that some inventor will have his or her best ideas, somewhere between 6 and 12. What's the probability between 12 and 6? All right, so 966 inventors, and how many are in that group? 135. All right, so how about 135? So that's it. That's the probability. Now, we don't have to change it to a decimal, but I think this book is asking us to do that. So if I write 135 divided by 966, here's what I'm getting. 0.13975 dot, dot, dot. How about if we round this off to 0.14? So 14% of inventors get their best ideas between 12 noon and 6 p.m. All right, I think you can see how the other ones are going to go. We don't need to do everything here.